I think you all remember the DynoBat series, and I finally found some time to pick the project up again. So this is the DynoBat as it is right now. Um, I transferred the circuit like it was from the breadboard to a little PCB board pre-drilled, and I shortened all the leads and all that. And aside from making it a little bit more compact and a little bit clearer as to where all the parts are and cutting down on all the wiring, it also had an effect on the frequency of the astable multi-vibrator. As you can see, the frequency dropped from 99 Hz to 83.8, well, let's say 84 Hz. Now, I'm not a high frequency specialist, but in my opinion, the drop in frequency has been partially because I shortened all the leads and I cut down on all the wiring and all that, and that I'm almost certain must have had an effect on the frequency of the whole circuit. So, but the drop in frequency didn't have that much of an effect actually, and if anything, it improved slightly the efficiency of the circuit. Now, for those who pick up the DynoBat series now, I'll say that I used an astable multi-vibrator, which means it's a vibrator or oscillator circuit which generates square waves. And at the output of the oscillator, in fact it has two outputs, either at the collector of one transistor or at the other. The output, as you know now, is a square wave. I attached to the output a low-pass filter, as you can see explained here. And the low-pass filter has the effect that the signal in effect changes from a square wave to something which resembles much more a sinusoidal wave, something which I wanted to achieve partially with this filter, because the transformer I'm using to pull up the voltage from V plus to high voltage was square wave, and I'm sure the transformer is not really built to handle square wave signals, but rather sinusoidal waves. So the low pass filter had a beneficial effect to change the square wave, but it also has a secondary role or effect, that it cuts all the frequencies above, in this case, 212 Hertz, which means that there are very little parasitic signals going into the base of the power transistor. Now, I'm sure the more observant of you will notice that there are two potentiometers, and the reason is that I reasoned that since I have the possibility of tapping off either on this side or on the other the square wave signal, I could just as well build a high voltage supply which would supply me on the one hand with around 65 volts and on the other 90 volts. Those two voltages are most currently used in the vintage radios I am used to repair. So, which is great. With one circuit I can generate two B plus voltages. So, namely 65 volts or 90 volts. Now, as you can see, at the moment I'm using the low B plus voltage setting, and I know it shows you 74 volts and not 65. But I reasoned that since the circuit has no load attached to it, it might be better to pull up the voltage just a little bit, well, in this case 9 volts to be precise, because I'm quite certain when I'll attach a load to the output, which is this part here, the voltage will drop. Okay, the other side generates a much higher voltage. Let me show you. So I switch off. There you go. And now I tap off the signal on the other side. Let's see. Hang on a minute. There you go. Okay, so now let's switch on the power supply. And there you see the voltage rising. So instead of 74 volts, the output will now stabilize around 99 volts, which again is about 9 volts higher than what it is supposed to generate. Okay, so it's 96 volts, 97. Well, the parts I use are not extremely accurate, so I tried to put the setting such that it would generate 99, and eventually you'll see it will stabilize around 98, 99 volts. So there you have it. Now, what did I change from the last time? Well, like I just said, I built in two outputs to the base of the power transistor, and I switched from using a BD139, which doesn't seem to be very solid or very efficient, to a 2N3055. That did a lot. It actually became quite easy to regulate, and it did away with a lot of trouble I had with the first version of my DynoBat. So yes, I use the power transistor. I also use a drop resistor between the base and the input of the signal from the low pass filter to the transistor. The drop resistor is about 1K, which seems to be in the Goldilocks zone of the 2N3055. So in effect I sort of biased the transistor, and now it works perfectly. And in fact it doesn't heat up at all. Neither does the high voltage part. So there's absolutely no heat generated whatsoever. So that's perfect. So there you have the signal. There you have the output voltage now from the high voltage part, the 90 volts B plus side. And the circuit is really perfect. I'll show it to you in a minute from both sides. Excuse me. What I did change at the B plus end of the circuit is that I added at the alternate current side, I added a small 10 nanofarad filter capacitor, and that in effect seems to have cleaned up the signal which arrives from the transformer, the secondary of the transformer, into the rectifier bridge. And it helps, it really helps. And I also mounted on the DC side of the rectifier bridge a 20 microfarad, let me see, is it 22 microfarad, 400 volts electrolytic to clean up the DC voltage. So there you are. It works really nicely, but I have to admit I haven't tested it yet on a load. So in other words, the real test will be to hook it up to a radio and see whether I can make a radio function from it. Undoubtedly, the rectifier bridge will get warm at that point, because right now it's at room temperature, and the voltage, like I said, instead of in this case 98 volts, will probably drop quite a bit. I wouldn't be astonished if it dropped 10-15 volts. We'll see. Right, so now I want to show you two more things, but for that I need to rehook the multimeter so that I can show you. So give me a moment. I want to show to you the input voltage that comes from the power supply which I use to power the whole circuit. Let's see. Voila. So now I put the setting on 20 and we switch on the whole thing. The input voltage is now, instead of 18 volts, which I used in the first version of the DynoBat, I now use around 9 volts. Well, as you can see, it's closer to 9.7 volts. The reason is that I reason that if I can put two 9-volt batteries parallel to each other to power this circuit, I will have a little bit more current to power it, and therefore I will extend the duration to which this circuit will function. In effect, now that the circuit is idle, I mean there is no load attached to it, it consumes about 35 milliamps. Now a 9-volt battery, a good 9-volt battery, will supply about 35 milliamps, maybe a little bit less, maybe 30 milliamps, or rather I should say milliamps per hour, which means that in at least as it is now in idle mode, it will work for about an hour, which is good, really good, and in effect that's what I'm aiming for, to be able to power a portable radio for at least an hour of music. So yes, there you go. Now effectively, of course, we will only know really how much power the circuit can deliver to a portable radio once I hook one up, and as soon as I'm certain that the circuit runs in a stable fashion, I'll be hooking it up to the Ever Ready, and therefore I'll be able, I hope, to finish work on the ever-ready radio. So, okay, I want to show you one more thing, so give me a moment. I'll hook up the circuit so that we can have a look at the milliamps it consumes.